Hello and welcome back. So if you remember the last video, we started looking into an example. We want to build a circuit that gives an output of 1 if the numbers or the combination of the numbers is greater than 0, 1, 1. In other words, 3. And 0 if it's strictly less than 3. Now, what would be the best way to show or to describe the behavior of that circuit? If you remember, we mentioned that we have the best way to do it is through a truth table. So here we have all possible combinations of the inputs. And then we're using this combination and show that whenever we're going to a number that makes a number in which the result is greater than 0, 1, 1, in this case 0, 1, 1, then we start having a 1 from then on. So if the number is less than that, and then we have a 0. Okay, so this F column here shows exactly the output desired for all possible combinations that we have. I also combine that with the inverted output. It's going to be very useful to describe two different ways to implement circuits and to define the behavior of a circuit. All right, so the idea is that we're going to be doing a circuit in which we have 3 inputs, A, B, and C, as we call from the truth table. And then we start then to drive the algebraic expression for that example, right? So how do we do that? Well, if you look into the truth table, see that if we focus on the outputs in which we have an output of 1 or truth, the function is going to be truth, true. We have, for instance, we have a 1 here in this row, 0, 1, 1, or 1 and 0 and 0, or 1, 0, 1, or 1, 1, 0, or 1, 1, and 1. So see that each row can be described using a and terminology. So this is 1 whenever this is 0, and this is 1, and this is 1. Or our function is going to be 1 when this is 1, and this is 0, and this is 0. Or when this is 1, this is 0, and this is 1. You see, within the row we describe with the and. So all this number has to be combined through and type of logic. And between the within the rows, okay, the function will be 1 whenever one of those rows is true. Okay, good. So let's see how we describe that and derive an algebraic expression for f. Okay, so all values that make the f1, I have to add the values, right? And then in this case, for instance, if I have this expression, A naught, B, and C is going to be 1 only when this happens. 0, A is 0, B is 1, and C is 1. So we need then to find all terms for which f is 1. And then you order them. As I said, this corresponds to each and every one of the rows. And then ordering all the rows, we have the complete expression. So for this particular truth table, we see that we start with this first term, and this first term can be described as A naught, B, and C. A naught and B and C. Why? Well, because we want this to be 1 whenever we have these 3 values. If you plug the 0 into the A naught, you will have a 1. And then B being 1, and C being 1 makes the A naught, B, and C 1, right? So, and then we keep doing that for each and every one of the terms in which we have a 1. If you see, the idea is that you plug here 1, 0, 0, and this term is going to be 1. So whenever either one of those is 1, we have our output equals to 1. So this is a way to describe in expression, Boolean expression, our truth table. Well, the other thing is that we may simplify this. So we already know certain rules and certain theorems to be able to make that expression and the circuit eventually much more efficient and much more fast and less costly, etc. So if we proceed to minimize that, we may, for instance, recognize that these two terms here have in common the A and the B naught, and the other thing is that the C naught and C are also they're part of the factor in either side. Therefore, I can apply one of the theorems. I can combine these two terms, these two terms. When I do that, okay, or I take the common factor here, and I know that what I get is C naught or C, and what you know, this is what? This is going to be 1. Same situation with these two that I put in purple. This is the case in which I have also common factor A and B, and C naught or C within the parentheses, which is this is 1. And at the end, well, getting this one and this one, this is the expression. You have in the book the same condition, right? We still can further simplify this, and of course, well, you can guess what the theorem we're applying here. Okay, so in this case, for instance, if I do again take A as a factor, then I get A times A and B, or the B naught, which is 1, and then that will be A, and here's the other term. Okay, so at the end, this is my simplified expression, A or B and C. A circuit for that, well, really easy. We already know how to do that. So we have an AND here that corresponds to this side of the expression, and I use exactly AND gate. And then the output of that will go together to do a OR with A. And this is what we need to do. Now here's another very interesting factor. So remember, we find the rows in the truth table that make the truth table equals to 1, or the function equals to 1. But I mentioned that I also explicitly provide the 0 column. In other words, if I invert the function, this is going to be the inverted functions, like having here a NOT gate following that. What is the interest for us to do this? Well, is to show that we can also, instead of working with the ones, each one of the rows that are 1, we can do exactly the same thing with the rows in which we have a 0. So instead of writing f in terms of the 1 of the function, we may also write f in terms of the zeros of the function. So if you put attention, you will see that the term A or B or C is going to be 0 only when all the 3 of them are 0, right? So if you find all the terms that are in this form, like a sum, right, that makes that particular row equals to 0, in this case, we will have this 1. So see that the first row, when we have A equals 0, B 0, and Z 0, that provides the A or B or C. It's going to be 0. Here, if we have A0, B0, and A1, then this is going to be 0. So that's equivalent to say, okay, well, we can sort of get an expression that is a product of sums, in which each one of the sum is found following this approach. So 0, in this case 0 or 0 or 0 for the first one, will provoke this to be a 0. 0, 0, 1, 0, 0, 1, then I have a 0. You see, I'm looking into the terms that make this function 0. Okay? So see, this is an expression that is a product of sums, whereas this one that we obtained is a sum of products. Each one of the terms here is a product. Okay? So very important that we keep in mind these two options. We are going to be using both of them to implement the functions. Okay. Okay. So the sum of products and the product of sum, we always can simplify. In this case, we can use some theorems. Usually I show in this form as the dual, kind of easier for us to see the sum of product and the product of sums. But it's going to be really, really important that we understand this really well. Sometimes you find that the best way to simplify is taking the form of product of sums. Okay, we apply some of the theorems here, and then, well, we can reach a simplification, right? So in this case, we can, if you see, we have the term A or B, which is going to be common, and we have, in this case, you know how to apply these theorems. Yeah, pretty much we arrive to the same expression as we had before. So the way we use either way or expression or sum of product or product of sum will allow us to proceed with some minimization strategies. Okay, so we can look into this expression and see that each one of the products that we extracted, because this is an extraction from the truth table, comes exactly from each and every one of the rows, and all the elements are there. So for each one of these products, you have the presence of the three variables in either direct or complemented form or inverted form. In this case, we have A complemented, and then B and C, then we have A, B complemented, and C, and so on and so forth. Okay, so that corresponds to a definition that we call mean terms. So each one of these terms in this equation or this expression is referred as a mean term. A mean term, if we have n variables, in this case we only have 3, is a product of n literals in which each variable appears exactly once, either true or complemented form, but not both. Okay, so in this case, I have only the presence of A once, presence of B once, presence of C once, and the same thing in each one of those. So in other words, you don't have any term in which you're missing one of the variables or the literal. Okay, so this is the concept of mean term. Okay, here remember, a literal is essentially a variable or its complement. So we can have mean terms, and also we can have max term. What would be the max term? The max term is the equivalent of the mean term, but given instead of product, we give that as a sum. And instead of providing, in this case, the 0, it will provide the 1, it will provide the 0. All right. Here's the table in which we're shown for instance, in this case, for 3 variables, A, B, and C, all possible mean terms listed. Okay? A naught, B naught, C naught, that will correspond to 0, 0, 0. Whereas in this case, that will correspond to the max term A or B or C. See that when in one of them appears complemented, in the other one appears in the sum non-complemented. So that is the dual. All right, that's the relationship between the mean term and the max term. 0, 0, 1, it will be A naught, B naught, and C. Why? Well, because if you plug this value of the input variables in here, you're going to see that a 0 into the A naught will give you what? Give you 1. The 0 into the B naught gives you 1. And the 1 into C will give a 1. So our term will be a 1, 1, 1, 1. Similarly, with here, we have a 0 for A or B, that's going to be 0. And in this case, we have a 1, and then it's simply move from 1 to 0. So 0 or 0 or 0 is going to be 0. Those are the terms that make the row 0, or the inverted function equals to 1. Okay? So, relationship. Each mean term has a value of 1, exactly one possible combination of that values for A, B, and C. Okay? Now, if my function is a 1 according to the truth table, in the row that I'm using, and it gives a 1, the mean term mi must be present in the what is known as the expansion of f, or the representation in terms of mean terms of the function f. Okay, so we designate the mean term mi to the row in the same order. For instance, row 0 will, that will be 0, 0, 0. That will correspond to the mean terms m0. 0, 0, 1 will be row 1, and that will correspond to mean term m1. So always you have that property is that any function can be written as a sum of products, right? Always, always, because that's the truth table. If you see something like that, this is what we grab from the truth table, right? Now, there's a compact notation for that, and when we use, for instance, we want to express the function in terms of mean terms, this is what we have. So in this case, that will correspond to the 0, 1, 1, right? In this case, this is a row that makes this term 1, and that will correspond to 0, 1, 1, it's correspond to mean term 3. 1, 0, 0 will be 4, and so on and so forth. Usually, we write this in order. And that's the compact notation is this one. Instead of using all terms, we use the sigma. Okay, this is a Greek letter that means sigma. Usually, it's used to addition, and then m, small case m, that means mean term, and then parentheses each one of the mean terms listed: the third, the fourth, the fifth, the sixth, and the seventh. All right. So this is, with this, we can build a function. We can build the truth table, etc., etc., etc. Same thing for the max term. Okay, max term corresponds to the zeros. In this case, I can say, okay, I can express that. Remember, in the table of max term and mean term, this corresponds to the max term given in capital M as 0. This is 0, 0, 1. This is M1, and this is the 0, 1, 0, which is the 2. Right? instead of using, we have a compact notation in which we, instead of using the sigma, we use the capital pi, and pi denotates product. All right, in this case 0, 1, 2, we have 0, 1, 2 with M capital and pi in front. See something. There is a relationship between the midterms and the max term. We observe the truth state, I mean the table, one or the other. If we're expressing a function in terms of mean term, if you see, well, my mean term in this case is 0, 0, 0, and that will correspond to a row in 1, then the max term is not present. So they are mutually exclusive. In other words, I can write my function either with a mean term or max term. So this is the max term. I was defining that. And each one of the sum or terms factors are known as max term. Okay? It's same, it's the dual of the mean term. Okay? Similarly, what happens with the mean term and max term of n variable in a sum of n literal will appear in each variable exactly once. Okay? Either true or complemented. This is what we call canonical forms. If you express a function in terms of mean terms or max term, you're expressing the function in terms of canonical form. Okay? All right, you see one example for that. Okay, see the following. If one of the rows is 0, then in the expansion or the expression using max term, this row corresponding to this max term should be present, similarly as what it happens with the mean term. Okay? Here, the max term mi is equal to 0 only for the combination of the values that makes this particular row equals to 0. So we can expand a function, a given function. Let's suppose that this is a function, and then we would like to expand that into a mean terms form. So because it's a 4-variable function, what happens in either mean term or max term? Well, all possible terms, mean terms or max term, they must appear all variables in each one of the product or the sums. So in this case, well, we can start trying to go into the mean term expression, but see something like that, A, C, and D naught, well, we're missing one variable here. We're missing B. Here we're missing C. We can actually, in this case, we need to proceed and then do the whatever we need to do to complete that. We can expand. We need to expand each and every one of the terms. Okay, so if we start proceeding with the associative here, it says we have A naught and B naught, or A naught and D, and this is the other term. But see, still, we need this term to be expanded so that have not only the assuming these two variables, but all possible variables that are related to this term, to the A naught and B naught. Well, because we have C and D variables, then we need to provide this term together with all possible combinations of C and D. So in other words, we will have for each one of these, of two variables, right, 4 terms. 4 here as well. And in this case, we need to complete with 2 possible variables of B, B naught, and the same thing with B. So here's the way in which we provide the expansion. Okay? One way is to say, okay, to this term, I simply provide these two, which are the two combinations of the variable C or C naught and D or D naught that are not present explicitly here. Okay? And the same thing with A naught and D. So in other words, we're expanding that. So remember, we're doing the inverse of simplification. We're expanding until we get all terms with all variables represented in each one of the terms. Okay? Here, because all we need is only b as a variable, then we have to take b or b naught. All right? So we proceed with this, and then of course you're going to find that we have repeated terms, and then we need to leave only one representative of this term. For instance, a naught, b naught, c, d is repeated here, and let me see, that's also in here. A naught, b naught, c naught, d, a naught, b naught, c naught, d is repeated here. And apparently there's no other repeated term. So we get rid of the terms, and this is what we have. This is what we have. This is the expression for the mean terms. We have the mean term 0, which is this, a naught, b naught, c naught, d naught. We have the 1, which is should be a naught, b naught, c naught, d. Where is that? This one is the first one. Then we have 2 that would be a naught, b naught, c, d naught, and so on and so forth. So we have all of these. Remember, 4 variables we should see from 0 to 15. Any possibility that we have here would be from 0 to 15. And of course, if you have this expression of the mean terms, what we have for the max term are all the terms that are not present here are here, and vice versa, right? Because of the table. Remember, a max term generates zeros, whereas the mean term generates the ones. So, and this is exactly the same function. So you have a set of zeros and set of 1. Okay, good. Well, I'm going to stop here, and we'll keep explaining max term and mean term. Very important definition to be able to do further simplifications and to understand much better the Boolean algebra. All right.